You're listening to Science and Saucery, a show dedicated to exploring innovative minds and adding life to your years. And now, your host, scientist Ray Cronise.
Welcome. Have a different kind of show today. It's just going to be me talking to you about oxidative priority. Had a fantastic weekend this last weekend with Jessica and Brian Kroc from Crocs in the Kitchen. So some fun things coming up with them. And I wanted to talk a little bit about a subject to go through and try to clear up some things. Recently I was on Instagram and I saw a post from, I don't know, this couple that's out there. I don't even know their names. And they constantly are using our graph out of the Oxidative Priority Paper and misquoting things and misattributing things. And they're in the keto crowd. They have all this information on the keto side. And it's really interesting to watch your own work misquoted and misappropriated, and especially when someone is just completely wrong. And then you watch a presentation on it and imagine someone standing up with authority talking about something when they really don't know what they're talking about. So if you want to get the Oxidative Priority Paper, you can download it at bit.ly/oxidative priority, all lowercase. Follow along with me a little bit. But I thought I'd go through the sections of the paper and talk a little bit about oxidative priority because it is misunderstood. So I'm going to do a little background as well on metabolism because some of the other graphs and other explanations need some background. But generally speaking, if we just start with the title, Oxidative Priority, Meal Frequency, and the Energy Economy of Food and Activity, Implications for Longevity, Obesity, and Cardiometabolic Disease. The whole point of what we were discussing with this is how calories are aggregated. So, I mean, this is a debate, an ongoing debate I was having with Dr. Michael Greger. You know, he would go through and look at this stuff and say, Ray, there's just not the evidence. And this has nothing to do with weight loss. So I'll repeat it again. I've told him over and over. I'll tell you over and over. This is really not about weight loss. And so anybody you hear talking about oxidative priority and weight loss, they simply don't know what they're talking about. So let's just start it right there. And the papers that are often offered up have to do with weight loss. And again, this really has nothing to do with this because how the body prioritizes fuels that are endogenous to the body, whether it's your glycogen stores or amino acids that get oxidized or adipose tissue stores, that physiology, it has nothing to do with this paper. It may have to do with other kinds of prioritizations of fuels, but it doesn't have anything to do with this paper. And I very specifically use the term oxidative priority to distinguish this from oxidative hierarchy that had been used before. One, because I thought it was more clear when we were writing the paper, and two, because it just sort of is a really good thumbprint of where people are starting from their research. So I didn't come up with this idea of hierarchical fuel storage and utilization. It actually goes back over a century. So it's not even a new idea. So it's, the argument I've had for many times is even for people to say, like Michael Greger, there's not the evidence. I would say there's a century worth of evidence that this is what we see. And interestingly, no matter how we look at the disposal of ingested calories, be it labeling or through mass balance, respiratory exchange ratios, it turns out they all come back to this general idea that our body utilizes calories that are ingested in an inverse order to the amount it can store. And so let me go through that a little bit more specifically. So when we think about eating, and you can think about animals being in a calorie scarce world, and humans were among that, we evolved in that calorie scarce world. And so it makes at least some sort of sense. And you probably heard last week's episode with Herman Podsner about this. It makes some sense that we probably prioritize fuels based on our ability to find them in nature and utilize them in nature. And of course, amino acids, contrary to popular belief, are really plentiful. Why? Because amino acids are the building blocks of protein, proteins, plural. There are tens of thousands of them in every plant and animal cell. And we have the same amino acids that make up plant proteins and animal proteins. And they may be in various concentration differences, but ultimately, we don't need much of them and we get plenty. And we talked a little bit last week about the study with the gorillas and their fruit versus leaf eating activity. So you can go back and listen to that and just know that finding amino acids in nature is pretty easy. You eat the plant or eat the animal that ate the plant, but the essential amino acids that you got to get from diet come from plants, and plants must synthesize them because plants can't eat. So this complete protein nonsense is just that. There isn't complete protein. This idea that only animal products have the indispensable or essential amino acids is wrong. All whole plant foods have all amino acids. Let me say that again. All whole plant foods have all amino acids. Now, that doesn't mean that those amino acids are at the same concentration. Doesn't mean that you might not have to eat more. A gorilla has to eat a lot more leaves in that season than when we're talking about the fruits to get the calorie. But what they found in that particular study was that the non-protein energy that was invariant throughout the season, and that protein just varied as it existed in the diet, and the highest level was when it was eating just leaves, the lowest level when it was eating just fruit, and it pretty much tracked a human low and high protein diet. So with that said, back to oxidative priority, when we look at that fuel in nature is pretty common as a fuel. And so we're thinking about this amino acid as something the body can burn. So we're talking about superfluous nutritional calories, but now those superfluous nutritional calories need to be utilized. And so what does that mean? Well, that means that if you think about it, when you eat anything, the fate of these calories, be it protein, carbohydrate calories, fat calories, exogenous ketones, we'll get in that later in this, alcohol, etc. If you can utilize it, basically the body has three choices. It can store it, it can excrete it and make waste out of it, or it can utilize it. And that's the three choices. We don't have much other choices. The energy has to go in one of those three buckets. And why that's important is because we can track all those buckets. And a lot of the people out there that believe calorie in, calorie out doesn't work. Now, I'm not saying that it's a very good, effective way to lose weight, to track calories, but I'm just saying that the idea that somehow we got it all wrong and calories don't work, most of the time, that's because they're not counting all the calories. And so in order to count all the calories, a person has to not only measure if they're doing indirect calorimetry, but they got to collect the urine because they have to look at what's gone in there. And normally that's going to be the nitrogen or the part from the protein. They have to look at the feces and what's in the waste there. You only have a certain amount of bile in your body for each meal. So the bile gets sort of used. And when the bile isn't sufficient to emulsify olive oil, that oil comes out. You can prove it to yourself. Drink a cup of olive oil. You'll see some olive oil in the toilet the next day. You will not absorb that entire cup of olive oil. So someone's out there saying, we got to be careful of oil because a cup of oil has 2,000 calories. This is somebody who's not thinking properly about oil because even if you drink a cup of oil, you're not going to absorb it all. And that's one of the explanations for why it appears that a high-fat diet is more efficient, or eating fat causes you to burn fat. There's a number of other reasons people make that mistake. But the truth is that when you ingest it, your body has to do one of these three things: store it, eliminate it, or metabolize it. And that's just a fact. So we've got to start there. So when we go into the paper in our first section, in the introduction, the point that we're really making is that over a century, over that 19th century, by the end of the 19th century, we had learned that there are these fuels. By the beginning, around 1790 or so, when Lavoisier discovers oxygen, we learned that, hey, something was going on, that the flame of a fire was exactly the same as the respiration of a guinea pig. And he did this by putting the guinea pig and the flame at different times in a small ice-packed calorimeter that he named, and he collected the carbon dioxide air that came out, the carbonaceous air as they called it, but carbon dioxide air that was coming off of the flame and off of the guinea pig, and carefully measured that, and then also carefully measured the drips of water of the ice that was melting from the heat of the animal and the heat of the flame. And what he established is that they were identical. And so in that moment when respiration and combustion become the exact chemical process, we have a major change in how we're thinking about animals and how we're thinking about flames. In some sense, that's where this idea that food is fuel comes from. Before then, they really didn't think about it that way. And it's hard to imagine that we really didn't think about food as fuel in the same kind of way. Of course, they knew that eating was required for nourishment, but this was an exacting chemical relationship. And so not only did he discover that, but he also at the same time discovered that this compound oxygen existed. And so coming forward all throughout from 1790 really to the close of the 19th century, we see that all the research focus was on what are these fuels and how do we know? So starting in about 1834, when fuels were sort of segmented as protein, carbs, and fat, generally speaking, that's the first time it happens. And then a few years later, Justus von Liebig ends up doing it again and putting out his two main works, one on animals, one on plants, and carefully tracks, in the case of plants, tracks the minerals by burning some of the plant material and analyzing the soil, and again comparing that to minerals in, the minerals out, and then doing the same thing with animals, but instead of burning them, he was measuring these mass changes on various fuels. Now, Liebig incorrectly hypothesized that mussels only used proteins. He falsely hypothesized that those were the only fuels of muscular activity. And later, von Voigt, his student, proved that to be incorrect. So as we move forward through the 19th century, one thing that we find is that we refined how we measure and how we burn fuels. So by the time we get to the close of the 19th century, this is a time when Rubner comes in, Pettenkofer, Atwater, people have heard of Atwater, then some of the other greats, Lusk and a number of others. But by the time we close the 19th century, what we find is that we now know there are these categories of fuels, that there are these things called proteins, plural, that these are things called carbohydrates, plural, that there are things that are lipids or fats, plural, and then there's this alcohol. And a lot of very careful work went into doing this with calorimetry. So let me take a sidestep now on metabolism, and let's talk about that calorimetry, because that's going to go into figures 1 and figures 2 in this paper. So if we back up a little bit and say that when you had high school chemistry class, if you had it, or if you've had any chemistry class, you might remember the exercise when you balanced an equation. So generally speaking, we represent molecules or these fuels that we have with their atom constituents. For example, in the paper, you can see in figure 2 that there is an example of ethanol, which is CH3, CH2OH structurally, and people who've taken organic chemistry probably understand what I just said. But ultimately, what you find out is there's 2 carbons, there's 6 hydrogens, and there's 1 oxygen in ethanol. And then in order to completely combust that, to react that with oxygen, which is what Lavoisier discovered in terms of combustion, and it doesn't matter if you burn it in an alcohol lamp or it's being metabolized in your body, this chemical relationship, it's called stoichiometry, of reactants and products is going to be identical, which means we need 3 O2 oxygens, these are the diatomic oxygen molecules, to react with 1 molecule of the ethanol, CH3, CH2OH, and that's going to produce 2 molecules of carbon dioxide and 3 molecules of water. So as you see it written under section A there, you'll see it C2H6O plus 3 O2 yields 2 CO2 plus 3 H2Os. And if you do the arithmetic on either side, you'll see that they balance. You'll see that there's 2 carbons on the left and there's 2 carbons on the right. And you'll see that over on the left side, there is, let's see, 6, 7 over here, and you'll see that they're over there the same. So as you add these up, you're just multiplying the little coefficient, the 2 and the 3, times the little number that's beside it. As you add these up, they balance out. Now, what's exciting about this is it's very much an arithmetic relationship, meaning it's something that you don't ever get a half of a carbon dioxide. You don't ever get a portion of this. You get a relationship. When a molecule of ethanol burns, it consumes those 3 moles of oxygen. And what I did in this particular paper, because this comes up so often, is I just solved the linear algebra equations. It's not that difficult. It's tedious. But I created general equations so that if you had any number of C's and any number of H's and any number of O's combining with oxygen, that these coefficients A, B, and C could be easily derived by a relationship. And that's what all those X's and numbers and coefficients are in algebra. And so anybody who's done linear algebra knows what that is. I just solved those equations. And so down below in that small little chart, I'm showing that when you put in any of these numbers, for example, glucose or fructose, so those are isomers, so they actually have the same number of carbons, hydrogens, and oxygens in them. The same with lactose is a little bit more. I put in there 2 ketones, beta-hydroxybutyrate and acetoacetate. And the reason why I did this is because I believed that once I got out there, that some of these people that were going into this keto diet were going to end up doing this. I thought it was silly that they would do it, but I hypothesized that they would, or let's just say I guessed that they would. And I put this in as a stopgap measure, and we'll come back to why that is. And then, of course, these are just various chain lengths below that, capric acid, lauric, linoleic. These are just different chain lengths and saturations for lipids. So these are fats. So you see some ethanol up there, you see glucose or some examples of sugars, you see some ketones in there, and then you see some lipids. And then the albumin is an example of a protein. So why is this important? Because if you look on the column all the way to the right of this paper, you're going to see RQ, or it could be called RER, depending on your textbook. But what you'll find is that when you do the ratio of the carbon dioxide produced, that's the little number, back to the ethanol example, that's the little number in front of the CO2, the 2, divided by the oxygen consumed, which is the little 3 in that equation, you're going to find that alcohol has this respiratory quotient, or RER, of 0.67. It's a number. It's a relationship. So this is not something that is different person to person, animal to animal, or even animal to plant. When you oxidize ethanol with oxygen, or even in a flame, if you have an ethanol lamp, and I'll tell you more about that, you're going to get 0.67 in terms of the ratio. So when you have a calorimeter, there's really two different types, and we talk about this in this first section. The first kind of calorimeter is one called a direct calorimeter. Now, calorie is related to that whole root temperature idea. So what one does in a direct calorimeter is you put a person in a sealed box. You then are able to measure the quantity of oxygen that you're flowing into that box, or air, and you know the concentration of that air going in. You're able to scrub the air that's in the box with a compound. In this case, probably lithium hydroxide is common. That's what they used on Apollo 13, if you ever remember this whole sample when they were using the air scrubbers to survive their trip back in the LEM. But anyway, you use a compound that reacts with the carbon dioxide and pull it out, and you can measure the weight of that. So you have a direct measurement of the carbon dioxide produced. You also have the amount of oxygen that's consumed because you know how much air is going in, and you can analyze those things. And then what you measure, which is why it's called direct calorimetry, you measure the temperature of water that's going in and out of the walls. And so in these direct calorimeters, the walls are made of a metal with a tubing in them. Very accurate temperature thermometer on the input side. Water is going in at one temperature. It's circulating through the walls, and you as a human sitting in there, or an animal, or a flame in the case of an ethanol lamp, I told you we would talk a little bit about that, is going to heat up the room. Now, generally speaking, we're about 80 or 100 watts in terms of our power output as a human. What does that mean? You're like an 80 or 100 watt light bulb. So if you can imagine taking a 100 watt light bulb, doesn't work with LEDs, but the old incandescent type, and putting it in a box. Maybe you made an incubator for chicken eggs when you were small, or maybe you made a heat box to cure some resin if you're doing car work or heating up something. But the idea that that lamp or that light bulb gets warm, and the energy that's coming off of that lamp is heating that space. And if you could imagine that you put that light bulb in a sealed, insulated box and ran water through the walls to pick up that heat, that the water in would be cooler than the water coming out. The light bulb would effectively heat the water. And so that's exactly what they did a century ago. In fact, that's what they did 2 centuries ago. They were using that heat. Remember, coming back to the idea of the guinea pig and the flame, Lavoisier was using the weight of the ice melted to be indicative of the amount of heat that was generated by the guinea pig or the flame. And this becomes really, again, it builds confidence in the goodness of our model of the world. And why is that? Well, because I can take an alcohol lamp and put it in a bucket and then put a nutritional hood, the same one I would put over myself if I was measuring my metabolism, and I can sample that air over that alcohol lamp, and I will get the carbon dioxide that that alcohol lamp flame produces. In fact, I've done this with an alcohol lamp. I've done this with a oil lamp. In fact, you can make an olive oil lamp. You can look on Amazon and whatever, you can find them that actually is burning olive oil. You can also use a soy candle. Now, soy wax is just a lipid. This is the fat from soybeans that has been changed into that waxy material of the candle. And so you end up with this waxy substance, which is just a fat that you can burn with a candle. And in fact, it's so accurate that I created a candle when CBS News came one time to interview me, where 3 of the wicks exactly matched my resting metabolism rate, and burning only 2 of the wicks matched the CBS correspondent's metabolism, which is really kind of interesting. So that means I could light this candle, put it in that bucket, light 2 of them, and it would be her metabolism level, light 3 of them, and it would be mine. And this is within about 100 calories. So it's a pretty close thing. It also means this: when I was fasting and my metabolism was burning 96, 97% fat because I was on a long-term fast, if I light this candle and put it on a scale, and then I put myself on the scale, that the candle and me would be changing weight at exactly the same rate. Now think about that for just a minute. When you're losing weight, if you can imagine that the rate at which you can oxidize or metabolize this excess fat is about the same rate as a candle burning. How long does it take a candle to burn all the way out? And this is one of the problems with, especially with my clients that have more than 100 pounds to lose, because it's just inconceivable how much energy that we can store. It's fascinating from an evolutionary anthropology perspective, because it's why we've survived so much, because we can store this energy. But it's really sometimes psychologically limiting from a weight loss perspective, because there's just so much energy in our metabolic bank account. So getting back to the calorimetry, when I'm measuring my metabolism or one of my clients' metabolism or doing metabolism work for research in my lab, I'm doing indirect calorimetry. So what is indirect calorimetry? Well, that's back to what I told you the first direct part was, where you're actually directly measuring the heat. You're directly measuring the thermodynamics of the situation. And you're also measuring the oxygen and CO2. And so by doing that, we're able to get an exact number on the heat. And this will be important in a minute. When we're doing indirect calorimetry, we're measuring the CO2 that's exhaled and the oxygen that's consumed. And you can do that on a breath-by-breath basis. Or if you're doing a lot of activity where it's going to be going up and down, you'll breathe into a bag and collect a sample over, say, a period of time, say an hour or 15 minutes, and then analyze that whole thing. Effectively, the bag becomes an averaging for that time. Or if you're doing it, for example, in a room, you're really averaging it over a lot of time. And why that helps is because every breath is changing so quickly. And so averaging it over time makes it a little bit, it's a mechanical way to average all the data points. You can also average it with arithmetic, but there is an advantage in terms of rapid response and sensors, et cetera. There is an advantage to using a mechanical way of averaging, meaning one of these chambers. So often, if you've actually had your metabolism measured on a bike or on a treadmill, you'll see that the mask that they're using often is actually going into a chamber, and then that chamber is where the sensors are, and that's doing it. In the case of a metabolic hood, if you've ever seen the pictures I've posted or seen other ones where there is a bubble over the person's head, that bubble basically just takes every breath by breath and puts it in there, and there's a fan slowly removing that air out and just measuring it over time. So again, this is a way to mechanically average all the breaths so you get a better snapshot of what does it look like over time. So that's indirect calorimetry, measuring carbon dioxide and oxygen directly. It's so easy to do with sensors today. You get a cylinder of calibrated gas. So I have these cylinders of calibrated gas that have exactly this amount of parts per million of CO2, exactly this amount of parts per million of oxygen. And then when I sample that, I know exactly that my sensors are reading correctly. I then have a calibrated syringe. And that syringe has exactly 3, I think it's 2.99 something on my certificate, but each pull of that syringe is calibrated in terms of volume. So I do that in and out and make sure that the thing that's measuring the volume, it's a small little turbine that turns and it counts the clicks, but making sure that the volume that the person's breathing in and out, that the volume is correct. So if you're accurately measuring the volume and you're accurately measuring the carbon dioxide and you're accurately measuring the oxygen, coming back to the equation in figure 2, section A, you can know what is happening when you're metabolizing ethanol. As well, another way to calibrate a calorimeter is to put one of those ethanol lamps in there with a known amount of ethanol, light the flame, weigh it when it starts, weigh it when it ends, collect the data of the oxygen and the CO2, look at the respiratory ratio that it predicts, and boy, the line is just a perfect 0.6667. It's always just perfect. It's fascinating that it's that way. With a candle, it's always like around 0.7, exactly that way. So you actually measure that and measure the weight of the alcohol change. And by that, you can say, okay, was the magnitude right? And to give you guys an idea, it's around 5,200 kilocalories in terms of what a 24-hour burn would be. So one of those little alcohol lamps that you would have in a chemistry lab, and I'm not talking about the butane burners, I'm saying the little tiny lamps that have the wick in them, kind of came in a chemistry set. The energy equivalent output of that is about 2 human beings worth. So it's going to be about 5,200, where a human being is going to be somewhere around, somewhere between 19 and 2,400 or so. This is just in terms of basal metabolism rate of a human. So that little alcohol lamp is burning twice the amount of energy as a human. So why is this important for the beginning of this paper? Well, it's important for the beginning of this paper because what we're doing here isn't guesswork. This is not guesswork. This is a relationship that is easily validated. It's a relationship of thermodynamics that we know works. And all these people that are trying to say that calories in, calories out don't work, these are people who just aren't measuring all the calories. Because 100 years ago, when metabolism was cutting edge science, they very carefully measured the urine, the feces, the direct calorimetry, meaning that temperature difference, the carbon dioxide, the oxygen utilized, and it worked. And in addition to doing that, and you see that in the introductory section, Atwater went on to measure some 4,000 foods with protein, carbs, and fat. So he had the protein, carbs, and fat. You guys all know I call this macro confusion, and this is, I don't think, a way that you should classify food, but he did it back then because these were classes of organic chemistry molecules that had similar functions in organic chemistry, and they clustered them together. Why? Well, because exactly what you see in that figure 2, because when you look at the structure of them and the oxidation of them, they generally fall in a pretty close range. And maybe to look again at table C in figure 2, if you pick that up, you'll see that all of these different amino acids, and I bold, the ones that are bold are the non-essential, the italicized are the essential amino acids, and you'll see that they all average around 0.84. They average around 0.84, but you can see they actually have, if you look at the individual one, you'll see aspartic acid, for example, would be 1.17, whereas one that's really low, let's see, what's one really low? Methionine is 0.6, okay? But averaged over all of them, it's around 0.84. And then, of course, go back over to B, table B, and look at the very bottom, albumin. Albumin measures at about 0.82. Now, a wide range of proteins are going to have a wide range of amino acids distributions, but on average, they're going to be about between 8.82, 0.85, etc. So why is this important? What's important because glucose and carbohydrates normally measure 1. You see that in the table B. And all of those fats down there, if you were to average all those are about 0.7. And it's very convenient for us but it's of no real reason. It's not an explanation for something. It's luck of the draw that what's halfway between 0.7 and 1. And remember, these numbers that we're talking about are ratios of carbon dioxide to oxygen. So in the case of burning glucose or sugars, carbohydrates, it's going to be 1, meaning for every molecule of CO2 that you generate, you're consuming a molecule of oxygen. Whereas with lipids, it's 0.7. Right? So why is 0.7 and 1.0 convenient numbers compared to protein? Because protein is really close to 0.85, which is the halfway point between those two molecules. And this is the only reason indirect calorimetry works. The only reason that indirect calorimetry works is because 0.7 and 1 on a scale, meaning fats and carbohydrates, happen to be divided right down the middle with proteins that are around 0.85, which would be the center point. And normally we control the alcohol content because we don't give people alcohol before they do a metabolism experiment. So we don't have the 0.67 ringer. But even if we did, that would just bias it down. So what happens essentially, and I know this concept's going to be tough for some people to visualize, but what it means is that the protein that you're metabolizing at any given minute will raise your overall metabolism up and down. But when we're asking what is the fat or carbohydrate that we're burning at every given moment, those two aren't impacted. That ratio isn't impacted because protein is right in the center. It's at the middle, at the teeter-totter. So if your metabolism is 2,000 calories and 10% of that is protein, so that's that 200 of that, and the rest, the balance of the 1,800 is half carbohydrate and half lipid, each one of those will be contributing the balance 900 calories. Conversely, you might be burning 1,000 calories of fat or carbohydrate, doesn't matter, take your pick, and 900 of the other one. Or you might be burning 1,800 of fat and no carbohydrate, or vice versa. Meaning we can actually see by what that number is between 0.7 and 1, the average, we can see what is the ratio of fat to carbohydrate you're burning. And this becomes really useful in the lab. And it would only work if it just so happened that from a arithmetic relationship of the stoichiometry of consuming a protein, that protein happens to be right in the middle. So what do? How do we correct for the protein metabolism? Because clearly all the foods that we're eating and all of these metabolic ward studies and all the things that a person's doing, if a person's running on a treadmill or doing a power test on a bike and wants to see what their VO2 max is and also wants to look at the metabolic burn rate, well, the point here is that we actually use urine. So as we metabolize a protein, the metabolite of protein metabolism, meaning we pop off the amino group from the amino acids, that amino group ends up forming urea. And urea is the main component in urine. So if we analyze someone's urine at the same time, we can see during that 24-hour period how much of the energy that they metabolized was protein energy, because we can see it in the urine that came out. We can also then measure the CO2 over the 24-hour period. We can measure the oxygen over the 24-hour period. We can also collect their feces and measure the lipids and anything that might be in the feces. And through all of that, back to what I said, that calories count when you count all the calories, all of that would come up pretty close to zero and balanced. And I have probably 20 books and studies, very long, detailed studies with hundreds and hundreds and hundreds of experiments that were done. And they all add up. The out-order factors are pretty close. So if they're pretty close, why is everybody still confused about protein, carbs, and fat? Well, there's one more factor that we put in here that needs to be taken into account, which is when you chew your bagel and cream cheese and maybe lox and bagel or whatever the heck you're eating for the moment, your vegan chili or your whatever you're eating, when you chew that and digest it, not everything is digested. For example, cotton is a carbohydrate. It's cellulose. It's just glucose. Cotton is made out of glucose. So are 2x4s. Lumber, if you go down to Lowe's or Home Depot and grab some wood and grind it up, that's just a bunch of glucose. But the bond that holds that together, that holds cellulose together, the alpha 1,4 linkage of starch versus the beta 1,4 linkage of cellulose, what you end up having is that those two bonds take a different enzyme to break them apart. So while there's glucose in that tree, and that's why termites can eat wood, or glucose in that cotton, we don't have the ability to access the glucose, but certain organisms do. And in the case of animals that are eating a bunch of grass with a bunch of fiber, they have organisms, bacterial, a microbiome in their rumen that's fermenting that. A lot of it's being fermented to other kinds of short chain fatty acids, but that's a whole nother story. But the point is that glucose, the energy in that fiber is liberated. Whereas for you and I, the fiber is going to go through. And at best, something in our microbiome might break down some of the fiber, but most of it is going to go through. So if I measure the carbohydrate content of a meal before you eat it, and then you eat it, and I don't collect the feces and measure the fiber that came out, the dietary fiber that you didn't digest, then I'm going to attribute some of that energy to glucose that you never saw. Conversely, if you've ever eaten a mushroom or a corn or other things that you see in your feces when you go to the bathroom, we all look, it's okay. That undigested material is there. Now, how do we measure the calorie content in food? Well, today, what most companies do is they do an analysis of the food. They do with the general analysis of protein, carbs, and fat, and they use standard factors, and that's how they come up with the labels. Back in the day, when Atwater was doing this, they would emulsify the food, dehydrate the water out of it, and they would burn it. And they did it in a thing called a bomb calorimeter. Now, when I was NASA, I would say this was probably one of the worst jobs I had while I was there. So one summer I was working in the thermo lab and I was doing calorimetry, and we were using composite materials, which are carbon-based or carbon phenolic materials, which are basically resins. Kind of think about fiberglass in general if you've worked on boats or other things, but these are more advanced ones we use for aerospace. And they wanted to know what the carbon content was of these materials. And what we would do is we'd have that material, we'd start out, we'd form the material, and then we would pyrolyze it. And that is sort of heat it up really hot in the absence of oxygen so it didn't burn. And it would actually create this carbon framework. And this carbon framework was really strong. So when you see carbon fiber golf clubs or carbon fiber panels on cars, that carbon fiber mat is what I'm talking about. But we were making entire nozzles, rocket nozzles out of this. And my job was to look at how much material was in the starting material and how much was in the end. And so you do this in a bomb calorimeter. And what that does is you take that small sample, you weigh it very precisely, you dry it, you put it into a small device. It's called a bomb. It's a little steel cylinder that's sealed up. You charge it with a known amount of oxygen to a certain pressure. You put it in a tank that has an exact temperature, and then you put a thermometer in this thing, in the water that's surrounding the jacket of this bomb. And you wait for many, many minutes, sometimes an hour, whatever, for it to come to thermal stability so that the temperature is not moving. It goes to an exact temperature. And then you push a button. When you push a button, an igniter goes off inside this, hence the word bomb. And because the carbon samples are, or if it was bread or dehydrated, think about your average camp or survival food that you just ground up and as a powder and you put it in there. If it would burn, then you could make this burn. So even aluminum burns. If you think about it, the space shuttle had the solid rocket boosters, and those two solid rocket boosters on each side used aluminum for fuel. So you can even burn a metal, or people maybe have seen a sparkler where magnesium is burning. So the point is, when there's a lot of oxygen and there's heat, lots of things will burn. And that's exactly what we did. So we would burn it, and it would burn it completely. Well, of course, if you're burning this inside this big metal cylinder, and you know the mass of the cylinder, you know exactly what the energy content was of the little igniter that started the fire, and then the water would change temperature, and you would have to sit there for an hour and watch this temperature go up and up and up and up and up and up to a certain point. And then when it got to that certain point and started going down, you had to make sure not to miss that. That wasn't the time to go to the bathroom, or you had to start all over again. You needed to see right where it stopped, write that temperature down, and then get that. Now, they also make systems later that do all that automated. So you don't actually have to watch it. You push the button and walk away, and it just measures the temperature. But the system I had to use, a power bomb calorimeter, used a very, very accurate thermometer. And my advisor at that time thought it was really good that we do this the manual way because it is very accurate, doesn't make any mistakes. And so I had to do this hundreds and hundreds of times. And yes, I did samples of lunch, I did samples of soup, I did samples of all kinds of fun things, because if you're going to be doing this, why not do other things as well? But that's how much energy you get if you burn it. And we just said, if you burn cotton, you would get, for example, a certain amount of energy, but I can't and you can't digest cotton. So you're going to get a different number. And so that would be the metabolic coefficient or the digestibility coefficient of this. So all of these meals have this amount of material in them. And this amount of material, if burned in a perfect condition, will make this amount of energy. There's no question about all those things. However, there is a question about what was the digestibility factor. And we all know, having seen, probably those of us especially that are gulpers, having seen pieces of food in your stool, you find out that obviously even how much you chew matters. This is another thing about drinking smoothies all the time and blending food. Just increases the digestibility. A really good thing if you have a geriatric patient in the elderly or someone who doesn't have teeth and can't chew. Very good. Very good for a baby that's just getting on solid food to eat that blended food because it's much more digestible. Probably not a good idea if you're trying to lose weight. Maybe okay as a liquid diet for someone who's had a bariatric surgery and their digestive tract has been surgically rearranged. Something I don't support. I think it's far more humane to teach a person not to swallow. So where we are with all of this is that these ratios of carbon dioxide and oxygen that we can measure in a lab with indirect calorimetry and that I do with my Cosmed Cork CPET or KB4, the KB5, these are really accurate numbers. And the labels on food are okay, but they're certainly not perfect, which is why I tell everybody to ignore calorie labels. It really doesn't matter. If it doesn't add up, it's not that your body is broken. It's not that you're wrong. It's just that a combination of the digestibility factor with the fact that whoever in the world put together this sample, what was the size? Do you really believe when you go and get an Impossible Whopper at Burger King, do you really believe that that Impossible Whopper is exactly the same made every single time as the one they gave as a sample? Might there be any advantage to a company that's measuring the food that's going on their menu? Might there be an advantage for them to underestimate the volume that's on the plate so that the label, the mandatory calorie label that goes onto the menu is a lower number? And might it be also, when ingredients aren't that expensive, common for them to put more on your plate so that the customer is happy? You see, there's a lot of reasons why all the calories aren't counted, But this is that first part of the paper. And this is a part that I need everyone to understand, that these are arithmetic relationships that we can measure pretty well. This is not contestable. There are errors in it, and there are error bars in it, but all of those error bars over the last century have done pretty well. And this is going to become important later. So where we are generally in the paper is I've talked a little bit about up through page 8 on this paper. I've talked about figure 1 and figure 2, and I'm going to go back to figure 1 more specifically here in a second. But what it means is that when we lock people down in a metabolic ward, it doesn't matter that there's not 100,000 of them. The sample size isn't as important, because every single time we feed either 1 or 2 or 3 or fast fewer people, we always seem to get the same answers. We don't get very many different answers. 382-day water fast, 276 pounds over 382 days, 0.72. Jake Rader, 2 or 3 episodes ago, 110 pounds over 149 days, 0.722. We get about the same answer. That's about the amount of energy that a human being is, and it's not that far off from what we see. So now let's look at figure 1 for just a second so that we can see what are we talking about here. So what I'm trying to say here is that measurement of the carbon dioxide produced and the oxygen consumed and the actual total energy of that, because we also use this to calculate the total energy that is actually being done, that energy is composed of a lot of different things in the body. So first of all, are you warm or are you cold? If you're pretty warm, it turns out your body doesn't need to burn as much energy to stay 98.6. And in fact, you're having a lot of evaporated loss because you're sweating and the water is evaporating. Again, thermodynamics, the water is evaporating. And for you people that have studied thermo, you guys know this, delta G equals delta H minus T delta S, that enthalpy, and that gives free energy. And if the entropy is going up, that temperature has to fall to keep that equation balanced because nothing else is happening during evaporation. If you didn't get that, it's okay. But for those that are following, that are on there, that's the case. So in other words, but we all know, this is this whole thing that got me started in this. If you're cold, your body's going to burn a lot more calories to stay warm, right? This is exactly the analogy that I was using with the light bulb, lighting up the box and measuring the temperature, water temperature in and out. So that first part, the EIT there, is the energy, the part of your metabolism that has to do with staying warm. So that's going to depend on the environment it is. It's going to depend on your clothing. It's going to depend on what you've eaten or what you haven't eaten. And then there's the exercise component. So this is, if you look at across the bottom, this is 24 hours. So these are little 1-hour blocks. So maybe you exercised for an hour. Well, when you exercised, what fuel did you use? Did you use fat? Did you use glycogen? How long did you exercise? And what happened when you exercised? You created that waste heat that left your body. Once again, if you were exercising in that box, just like we used to have people do in our space station mock-up, we had our environmental control and life support system that I was working on, where we were trying to pull moisture out of the air and look at reclaiming the water, reclaiming the air and clean the air. When we would pay our employees to exercise every day at lunch and eat lunch, et cetera, in these modules, and we would analyze that air and analyze that moisture content, analyze that heat content to say, okay, what do we need to keep space station for many, many years at a constant temperature and be able to reclaim some of the water? That exercise was going on for an hour. So now, moving forward, we look down here and we see, okay, every time you eat a meal, what happens? Well, when you eat a meal, your metabolism goes up, and then 4 to 6 hours later, your metabolism comes back down. This is diet-induced thermogenesis. And you've seen this. If you drink late at night alcohol, and you're laying in bed and you're hot and sweaty as that alcohol is being metabolized and your body's heating up, a lot of people say, I can't sleep if I eat a meal late at night. Well, what happens in that case? What happens is that you're burning a lot of energy. You're burning this extra calorie that you can't store, and your body, in order to fall asleep, needs to cool down. Your brain needs to cool down by 0.5 degree. melatonin is working to try to dump extra heat. You're probably in a warm bed. You probably got in bed. You probably covered up. And now your body's generating a ton of heat and you're waking up because of that heat. But every one of those meals has to be accounted for over this 24-hour period. And then, of course, what's your activity? Are you a wiggler? Are you a fidgeter? Are you sitting still? Are you just sleeping all day? And then what's the basal energy expenditure? And this is all of your organs and small things that are going on metabolically, your brain and the things that are happening. And what this little box to the right means is that each one of these things adds a little bit of energy to what your total energy is in that moment, in that hour, or over that whole day, since we all tend to want to average days. And then each one can shift your respiratory quotient, the number, up and down, right? Remember I said that up and down number, because protein is pretty constant and we can measure that part of it with how much urea you excreted in 24 hours. Then on the other side, we have the amount of fat you burned in that 24 hours and the amount of glucose or carbohydrate you burned in that 24 hours. And when we sum all that up, we get a daily metabolism. And this is where I think the biggest mistake is made, because your metabolic bank account, the amount of energy you have stored and the amount of energy you use, it's convenient to do a day-to-day summary when you're trying to do this sort of careful work and measure everything. A day is a good average period. Remember I was talking about mechanically averaging all those breaths? Well, in terms of the energy, this is done. And this is how everybody does. We compare the calories in and calories out in a 24-hour period. But that's a really bad way to do it in nature, just like your checking account. Imagine if the checks you wrote every day was based on the amount of money you deposited in that day. You compared money in and money out in your bank account every day, and you ignored your account balance. Can you imagine how complicated that would be? And so that really gets us into this thermodynamics of overnutrition, and this gets into the core about this idea of oxidative priority and why it's important. When we're looking at overnutrition, one of the things to think about, and I think the best thing to do, is to really skip ahead and look at figure 5, because I'm going to describe something to you, and then we can come back and look at energy and how we efficiently burn. And this becomes a problem in looking at food that's burning. You remember I talked about that candle? The candle that was burning with 3 wicks burning versus 2 wicks burning. When we look at figure 3, we get an example. And this gets into why when I talk to people about exercise, yes, it's misquoted. And you heard even with Herman Ponsner last week that he has the same problem when he talks about exercise, because we're not saying that there aren't healthy benefits of exercise. What we're saying is it's not a particularly good way to get rid of that excess metabolic bank account we just talked about. And the example here we have is, let's just say a person is sitting, and this person burns around 1,800 calories per day. Okay. When they jog and they run for 1 hour, let's say they run 5 miles, and a mile is about 100 calories a mile. This is just rule of thumb, not exact. But that 500 calories that they're now burning, so about 100 calories a mile, they're now burning 500 calories in that hour period. Remember back with our figure 1, that one little block of exercise? Well, this is a blow up of that 1 little hour of exercise. Now, anyone looking at this would say, okay, do you want to just sit and burn 75 calories an hour? Or do you want to jog for an hour at 5 miles an hour and burn 500 calories? Well, that's easy, because look at the difference there. That's 425 calorie advantage. But again, that's not the whole story, because the question that we need to ask is, where is that energy being pulled from? If that energy is 100% glucose, how much fat have you lost by that 5 miles of running and that extra 425 calories? Now, if you've already forgot the premise here, I'm going to remind you one more time. I'm not saying running 5 miles isn't healthy, etc. We're not talking about that. Okay, so I know a lot of people's brains go back to this idea that exercise is healthy. We agree. We're talking about, is this an efficient way to dispose of energy? And so when we look to the right at this fat utilization, notice at the bottom we have this respiratory quotient of 0.85 because a person who is fasted, meaning they haven't eaten in the last 4 to 6 hours, they haven't exercised, they're just sitting there, the person that's burning that 75 calories an hour, their respiratory quotient's going to be about 50% glucose, 50% fat. If you're fat adapted or eating a ketogenic diet or fasting, it's not going to be that number. I'm talking about a person who's eating a normal, balanced diet, and it doesn't even have to be equal. The respiratory quotient is going to be about 0.85, which means 50% of those 75 calories an hour are fat calories, and 50% of those calories are glucose calories or carbohydrate. So that's the 37 calories that we see there. Now, if you're running for that 5 miles, you don't just get to do the straight arithmetic and say, well, I'm just burning more calories. Because as you begin to run, your body starts pulling calories from different accounts. It starts pulling in glucose. So it turns out if someone's running for 5 miles an hour on a treadmill, their respiratory quotient, or that ratio, will go up to 0.96. And what that means is that of that calorie, only about 12.8% of those extra calories, or all the calories now, because it's a whole number, are fat calories. So you've really only increased from 37 fat calories an hour up to 64 fat calories an hour. And when we look at that, so that difference in calories is really, for comparison, it's about a half teaspoon of olive oil. A teaspoon of olive oil is about 40 calories per teaspoon, 120 per tablespoon, right? So we're talking about 27. So a little bit over a half teaspoon of olive oil. So that's what you get for running 5 miles in an hour. Again, we're ignoring the health benefits. We're also ignoring the injuries that people who are overweight get from exercising and causing knee injuries, etc. We're ignoring all of that for a second. We're just using energy disposal. And so what you're seeing here in figure 3A is that the benefit of increasing your calorie consumption from 75 calories an hour to 500 calories an hour is that you're really getting a marginal increase in fat. And that gets back to that idea that I said that the little alcohol lamp is about 2 humans worth, or that the candle is 3 flames versus 2 flames. It's a small amount. You're just not burning that many fat calories. And this gets back, we'll get into the weight loss side. This is why time burning fat calories is way more important than how many instantaneously you're burning. Now, in figure B, I'm changing this just a little bit, because in figure B, I'm showing that person who's sitting and burning 75 calories an hour, if they have been dieting for 2 or 3 weeks, and I've seen this over and over, their fasted respiratory quotient won't be 50% glucose, 50% fat, the way we see in example 1. It won't be 0.85. It will in fact be around 0.76 to 0.78, or about 75% of your rested calories are coming from fat. Now, those of you that have done the ketogenic diet, you would know that if you've been pulling out all of this glucose, it goes up a little bit more than this. in terms of fat calories. And we'll come back to ketogenic diet later, but at this point, just understand that that means of that 75 calories, 55 calories just sitting there doing nothing are fat calories. And then when I run, my respiratory quotient once again is going to jump up because now I'm doing explosive moves and the glycogen in my legs, etc., are still going to the same physiological mechanisms that caused the first example to go up are going to cause the second example to go up. The body's going to prioritize those explosive moves, whether it's weightlifting, aerobic activity, they're going to prioritize that as glucose if you have glucose available. And that's still that 64 calories. So now the difference, these 9 calories difference in running versus sitting is less than 1/4 teaspoon of olive oil. So a person who's been on a sustained diet for a couple of weeks, when they exercise, all of those numbers that are on the treadmill, a very small fraction of them are going to fat calories. And this is why I don't recommend exercise to lose weight. And even if 100% of these, and they're not ever in the case of a ketogenic diet, were fat calories, it still doesn't matter. Because if you're in that state, you're also eating more fat, so you have the ability to overeat by that 1/4 teaspoon. You have the ability to overeat. We're talking a 1/2 teaspoon. We're talking small quantities. So where I'm going is that it turns out that wiggling is not nearly as effective as not swallowing. And that's the way it should be. We should be optimized, since we evolved in a calorie scarce world, to be able to wiggle and run and hunt and gather and move with small amounts of energy relative to food. And we should be able to store energy in ways that makes it easy for us to move, right? A potato doesn't move very fast. A potato plant doesn't run, which is why it's a great source of food. You know exactly where to find it. You can dig it up. And these underground storage organs that you heard about last week from an evolutionary anthropology perspective, this is a food that was easy for humans to gather, and it's still easy for the Hadza tribes to gather. Way easier and way more reliable than a hunt. That doesn't say that they didn't hunt. It's just that those are a very big part of their diet, and that's why. And we as humans or other animals store fats in a more compact way, and we're able to move with them. So that kind of wraps up the input-output side. So at this point in the paper, what we've essentially established is that calories in and calories out count if you count all the calories. We've established that there are a number of ways to measure this. We can measure the direct thermodynamic, the heat, waste heat generated, and use that. We can measure the carbon dioxide produced and the oxygen consumed, and we can use that ratio to indirectly figure out what calories were burned and what the sources of those calories were. We know that because that ratio is like a thumbprint for alcohol, for glucose, for ketones, for lipids. And we realize that it's not good enough to measure the magnitude. So to use the car analogy, it's not good enough to use the speed of the car to judge the fuel tank when you have more than one fuel tank. If you want to empty the fuel tank, especially like if you're using an airplane where you have different tanks on the wings, in 0G, we have to balance this fuel. And so you take some fuel from one and then you switch and take some fuel from another. So my point is that absolute fuel consumption isn't the same from what compartment is that fuel coming from. Is it coming from the glycogen compartments? Is it coming from the fat compartments? So now getting back to figure 5, I want you to now think about the meal. And this is going to be important. And this is going to be one that whatever this keto couple is, it's always talking about and using our graph and They don't attribute it to us, or sometimes they attribute it to David Sinclair or to Andrew Bremer, whatever. But they're all talking. They're just the authorities on oxidative priority. But I can just tell you from watching their presentations, they have no idea what they're talking about. So if you're following that, you think it's all great. What you just heard is what has to do with weight loss. And that is, how do you run a deficit? The easiest way to run a deficit is to the exercise where you isometrically clench one's teeth in the presence of fattening food. You know, you keep those teeth really clenched down. You don't eat stuff. If you don't eat, your body has to burn the reserves you have on board, and it's great. So back to this chart on figure 5. If you look at the postprandial blood curves, what that represents is, I want you to think about an blood alcohol concentration curve, or I want you to think about a glucose curve, which means when you start eating glucose or sugar, your glucose goes up, and 4 to 6 hours, it goes back down. And when you're drinking alcohol, after the last sip, the blood alcohol starts rising up. And 4 to 6 hours, when they let you out of the drunk tank, your blood alcohol concentration's gone down. And the question is, where does it go? And so this becomes the foundation for oxidative hierarchy. This becomes the foundation for oxidative priority. And what it suggests is this, is every time you eat, whether it's a handful of M&Ms or a Thanksgiving dinner, your body then begins to digest that food. And as that food is digested in various parts of the digestive tract, whether it's alcohol, for example, or amino acids and proteins, or carbohydrates and glucose and sugars, or lipids, your body, and we won't go into details how, but your body extracts that energy out, and some, but not always all of it, ends up in your vascular system. So, for example, when I talked about earlier about that cup of olive oil, you're going to find that some of it's going to end up in the toilet. If you don't believe me, drink a cup of olive oil. It's disgusting, but you'll see it floating on top of the water. You're not going to absorb it all. And if you're on this ketogenic diet or a high-fat diet, part of the advantage is that you're swallowing a lot of calories, but a lot of those calories aren't being absorbed. And they're not being absorbed because you have a limited amount of bile that you're producing in time. Now, the downside of that is our bodies are adaptive and efficient. Remember, that wiggling was a very efficient way to move. This was something when I talked to Dean Kamen at SciFu in 2009 and Elon Musk about the Tesla and about the Segway. And for me, it was about the amount of Oreo cookies it took to go up 70 stories. Dean did the same calculation, and Elon did the same calculation when they were thinking about the electric car and the Segway, to say moving people-sized masses doesn't take much energy. The energy in 3 1/8 cookies to climb 73 stories in the downtown Weston. I did it in 20 minutes. I measured every single breath with a calibrated calorimeter, and that's all it took. And most of those calories, just like you saw in this chart, most of those calories were not fat calories. Most of them were glucose calories, carbohydrate. So climbing 73 stories of stairs didn't really make that much difference. Well, this is the same thing with a Segway. That's why their batteries work so well. It's the same thing with a Tesla when you start doing the economy and realizing that at some point, a gasoline or diesel engine, all of the weight of fuel and other things all start mattering. Yes, there are batteries with electric, but it just so happens that from an efficiency perspective, that moving people is mainly moving the cars. The people are sort of a rounding error in that. And so that's where they both use their engineering skills to optimize it. And it's where I'm using my engineering skills to optimize weight loss, meaning it's way more efficient not to swallow something than it is to believe that you're going to wiggle and mitigate that swallow. So when the body eats, you displace or you change your blood plasma concentration. You change the sodium concentration. You change the potassium concentration, the magnesium concentration, the glucose concentration. Your blood glucose goes up, it comes down. The alcohol concentration, the amino acid concentration, the lipid concentration. If you eat one of those high-fat diets and you take your blood 2 to 4 hours after your meal and you let your blood sit, you're going to see all this lipid settle out on the top of that blood. You've seen it on the movies that to talk about eating fats and whatever. But that energy is moved from your digestive system into your vascular system. And then from that vascular system, it's either metabolized, stored, or somehow eliminated. In the case of that lipid that we talked about, if you drink a cup of olive oil, it never even makes it into the vascular system. It just goes straight out the other end. So that's what this chart represents. And so the question then that was proposed is that when we have extra calories, where do they go? And what the oxidative priority suggests is that we will store those ingested calories based on the available storage space. And of course, where's the biggest bucket to store calories? It's the fat bucket. So when we ingest fats, and it doesn't matter if it's the small amount of fat that's in corn, because corn has corn oil, right? There's lipids in there, or soybeans, or eating a piece of bacon. It doesn't matter where those lipids are coming from, or throwing olive oil on your pizza. The point is, if you're able to absorb it, your body has, relative to any amount that you can absorb in a single meal, your body has an infinite storage capacity, because someone can easily be 50, 100, 300 pounds overweight. So you can store a lot of fat. So it becomes the lowest priority, because what happened? You just ate a meal. Your blood has now moved in its composition away from what its homeostatic normal is. All of these levels have gone up, and now for the next 4 to 6 hours, your body's saying, put everything back where it's supposed to be. And how do I put it back where it's supposed to be? Well, I'm going to store what I can store, and I'm going to burn what I can burn, and I'm going to eliminate what I can eliminate. But the body's trying to efficiently hang on to as much as it can. And it just turns out that that next level of storage capacity is glycogen. If you've just run a marathon, you're pretty low on glycogen. If you're in a ketogenic state and you've not eaten any dietary carbohydrate for weeks or months and you're really low and you've been a high level of ketones, your liver has a lot of room. Your muscle tissue has a lot of room. And that's why some of the low performance numbers happen in that state, because the explosive moves are slowed down. You know, when you're metabolizing lipid, for those runners that will know this, you can only use about 75% of VO2 max. When you're metabolizing glucose, you can do it completely anaerobically, because you can actually ferment glucose to lactate. So what does that all mean? Or when we're eating and displacing our blood plasma over that 4 to 6 hours of that meal, and that's the blocks that you'll see if you go back to figure 1, the dietary induced thermogenesis of meals. The body first packs away what it can, but unlike our simple model of metabolism, all the extra calories are not turned to fat. They're not. And how do we know that? Well, because we've measured it. And when we look at, one really good paper that was done by McDivitt and Prentice, when they looked at the idea of overfeeding someone with sucrose or glucose, and what they found that the amount of de novo lipogenesis, meaning when you overfeed with glucose or sucrose, and you look at what happens to that, how much of de novo lipogenesis, that is from new, lipo is fat, genesis is create, how much new fat is created. It says basically, even in the last sentence, it says quantitative, however, the absolute amounts of fat synthesized from carbohydrate did not represent a significant contribution to overall fat stores after 96 hours of excess carbohydrate intake. So that the amount of de novo lipogenesis measure is a minor fraction in the disposal of the other dietary carbohydrate. So what happens when you eat a lot of extra glucose? Meaning more glucose than you can stick in the glycogen stores of your muscle tissue and more glucose than you can pack away in your liver. So we're not talking about ketogenic diet now. We're talking about normal diet, someone eating an excess amount of dietary carbohydrate. I'm using the word carbohydrate in the real sense, so sugars and starches. What happens to that? It turns out that once those buckets get full, your body then starts switching over in its respiratory quotient and what it's burning, and just burns over the next few hours some of that glucose. And it can dispose of an enormous amount of glucose. You heard me talking about again this last week. 1,000 extra calories is only a bump of 41 calories an hour in your metabolism if the body had to expend an extra 1,000 calories of glucose that it couldn't store. It just means it's got to bump your metabolism by 41 calories. It's not a big number. Or remember when we looked at figure 3, we were looking at the ratio of glucose to fat in the rested state? Well, during this postprandial state, when this is in there, your body can easily shift 50, 60, 70% of those calories over to glucose calories and burn that off in a short period of time, in a few hours. Or you can go get on the treadmill and your body can crank up the glucose and you can dump all of that extra calories, mostly as waste heat. You can dump it in an hour. But it doesn't matter if those extra carbohydrate calories were burned in 1 hour with exercise or over 24 hours because of a small shift in your metabolism. Over that 24 hours, they still didn't get turned into fat. Now, it's true that they prevented you from burning fat that you would have otherwise burned. So back to my keto friends out there who have now trained their body to very efficiently take in lipids because they're fat adapted, which I don't know this is a very good thing. As soon as they put any dietary carbohydrate in their diet, their fat efficiency is high and the body just starts packing it away. And what do all your keto friends say? Oh, the carbs made me fat. No, they didn't. It was the fat they were eating before they added starches and glucose to their diet. And it's the extra bile they're now producing because we've got studies out there, vegans versus meat eaters and how much bile production is. And the vegans have lower bile production, which is actually good because they're not pulling even as much fat out of the diet. And we see this with fruitarians, that same sort of thing. So the idea here is that this response happens. Now, in terms of the amino acids of protein, even less room to store it. Because if you eat a pound of protein, you're not going to put a pound of muscle mass on. My bodybuilder friends out there, you guys know. Doesn't matter, male, female, on steroids or not. Putting on 5 pounds of muscle mass in a week would be really a lot. Putting 1 pound on is a pretty big deal. So what we're talking about is 463 grams in that pound. And of that 463 grams over 30 days, it's like 66 grams a day. So these are the numbers that people are eating. So all these people obsessed with all of this extra dietary protein in their diet. Well, one of the reasons why that works for what they're doing has nothing to do with the fact that protein is protein and muscle synthesis requires protein, because you might have had enough already. Gorillas don't have a problem synthesizing protein. Neither do elephants, neither do rhinoceroses, neither do giraffe, gars, hippopotamus. They don't have problems synthesizing muscle. And it's not because they're protein or amino acid limited. One of the reasons people like to use proteins or amino acids is because, like dietary carbohydrate, which after that first step of the deamination that goes on, they drop into the TCA cycle at the point that they're pyruvate. And for those biochem people out there keeping up with me at this point, there's absolutely no difference between dietary amino acid metabolism and dietary glucose metabolism. And neither one of them put on fat. Amino acids aren't efficiently converted into fat, i.e. de novo lipogenesis either. So both glucose and amino acids, whether you're the high carb people or the high protein people, both of them are right for the wrong reasons. And the reason is that neither one of those significantly convert through de novo lipogenesis during overfeeding into fat. But they are packaged with fat in different ways. And like I said, depending on how you've been eating, you might train your body to absorb that fat, and that's going to matter. And then when we get to alcohol, well, alcohol becomes this thing that has zero storage. And that alcohol that has zero storage ends up displacing even more. So much so that if you'll look in this paper, one of the papers we quote, they take glucose and inject it with alcohol. They first get a person's blood alcohol content at a certain level, and they inject that glucose directly into their arm. And what they find is that that ethanol increases the carbohydrate oxidation by 249%. And it suppresses fat to almost zero for 90 minutes after the glucose has been ingested. In other words, the body ends up needing to use the excess glucose and bring that back in level in check, bringing the alcohol back in check. And so what ends up happening is that because the body has to metabolize the alcohol to get it out of the bloodstream, because it's a toxin, it actually shunts fat burning. And here's where our brilliant exogenous ketone crowd is talking about, where they're totally missing the point. They're totally conflating a few things. And they take exogenous ketones thinking, well, this makes me more efficient at fat burning. No, it does not. What it does is displace the fat that you would have burned. So go back to that chart, go back to figure 2, go to table B, and you'll see that those ketones all have increased respiratory quotients. One of them is almost as high as glucose. The other one's almost 0.9. And by their logic, if I was taking these ketones, I would be going down towards fat. And in fact, exogenous ketones actually shunt you from burning those. So then why are ketones measured when I'm fasting, when I'm burning fat? Because ketones are an intermediate metabolite. They're a tertiary fuel. When you're not eating dietary carbohydrate, when you don't have those things in, and when you're metabolizing fat, and under a normal condition, the small amount of ketones don't matter, but they build up in the blood during times of low carbohydrate intake. They build up to a certain level and they spill out into your urine. So keto friends, think about this for a second. We evolved in a calorie scarce world. Why would our system evolve to waste precious energy, the intermediate of lipid metabolism, these ketones that can be used by other tissue, such as the brain, and spill it out into our urine just to waste it? And the answer is because it turns out that for many cells, it becomes a proxy for glucose. Tissues like the brain that can use that material don't have to consume glucose. And in the time of not having any food, the only source of glucose is, of course, is the gluconeogenesis that ends up happening from such amino acids like alanine and some of the other non-essential amino acids that are converted over, which means your tissue would be sacrificed to create the glucose, and then your tissue would turn around and use the glucose. But instead, those ketones can be used, but it's inefficient. But when you start swallowing them, they're just like alcohol. And they've modified this chart. You'll see this chart. You'll have exogenous ketones. If you see that, just ignore what you're seeing because they don't understand anything about this paper. They really don't get it. And it's sad to have to say that and be so point blank about it, but I've seen so many discussions about it. So if you see this chart, you'll see it on places like Mark's, Daily Apple, etc. And they've added to this chart that you're seeing, figure 5, they've added there's exogenous ketone, and they got all these stories. They don't understand it. And how do I know that I'm right about this? We're right about this because of something called Hess's Law. And for anybody out there that study chemistry, you'll know what this is. But essentially what it says is that when we calculate the energy produced of the system, that all we need to know is the reactants and the products. To give it another way is if I have a roller coaster and I start you at raising you up 400 feet at some high level, and I let you go, it doesn't matter what the humps and everything you do after that. The amount of energy you'll have at the very end can be no more in terms of the energy that was expended, the starting height and the ending height. And in a similar fashion, but not identical, chemical reactions happen in a similar way. And so what's really going on here, and why when I'm fasting, my resting respiratory quotient doesn't go up to 1 like exogenous ketones would be, even though my ketones are through the freaking roof when I'm fasting for 24 days. No, my respiratory quotient I measure every day is like 0.71, 0.69, 0.70. I'm burning fat. And because ketones are an intermediate, it doesn't rise up to 1. If ketones were a significant fuel, if that was the primary fuel, if this was the optimal fuel that everybody's talking about, then my respiratory quotient would go up, and it doesn't. When I drink alcohol, my respiratory quotient goes down. I've done that experiment. Does it go all the way to 0.67? No, because you can't get that level of oxidation, but it definitely goes up. And then when you're talking about exogenous ketones, I can imagine there's a slight rise, but the idea that has anything to do with you burning other lipids is just completely wrong. So, summarizing this table in Figure 5, what this really says is, as we eat these mixed meals, the body stores the things it can store, and it burns the things it can't store. And that the amount of energy that you pull out has to do with that digestibility coefficient that we talked about earlier, or how much bile is being produced, etc. It's a complicated relationship. And why is that important? Well, it's important because when all these people talk about the idea that somehow calories in and calories out is wrong, and yet the greats of nutrition and metabolism of the 19th century measured this stuff so carefully, and they got it right. And jumping all the way to the conclusion and reading this for everybody, Carl von Voigt wrote in a tribute to Max Pettenkofer, imagine our sensations. This is in 1901. He wrote this. Imagine our sensations as the picture of the remarkable process of metabolism unrolled before our eyes, and a mass of new facts became known to us. We found that in starvation, protein and fat alone were burned, that during work, more fat was burned, and that less fat was consumed during rest, especially during sleep. That the carnivorous dog could maintain himself on an exclusive protein diet, and if to such protein diet fat were added, the fat was almost entirely deposited in the body. That carbohydrate, on the contrary, were burned no matter how much was given, and that they, like the fat of the food, protected the body from fat loss. Although more carbohydrate than fat had to be given to effect this purpose. That metabolism in the body was not proportional to the combustibility of the substances outside the body, but that protein, which burns with difficulty outside, metabolizes with the greatest of ease, then carbohydrates, while fat, which readily burns outside, is the most difficult to combust in the organism. That's a century ago. And that's basically laying down the foundations of this oxidative priority on food that's been ingested. This doesn't have anything to do with the disposal of calories. What has to do with disposal of calories is Figure 4, the next section of the paper. And I'm not going to go into all of the details here, but basically just look at this. If you are fasting for 24 hours a day, and I really don't consider it fasting until you've been 36 hours because so many people are misusing this word, right? But if you're fasting for 24 hours a day, you're burning fat for that 24 hours most of the time. If you eat one meal a day, you're fasted now for 20 hours a day. So during that 4 hours fed state, 4 to 6 hours, but we round it off to 4 hours in our table. Your body is disposing of those calories by either storing them or prioritizing them to metabolize them. If you eat twice a day, then you're fasted for 16. You're fed for 8, and during that 8 hours, your body's trying to get rid of those extra calories, the extra alcohol, the extra glucose, the extra amino acids that it can't store. And all the fat during that period of time, not all of your fat, but all of the fat during that time in terms of the ingested stuff, body just puts it away for later. And for most of us, later never comes, because if you're eating 3 times a day, now I'm not assuming any overlap here, but if you're eating 3 times a day, again, 12 hours fasted, 12 hours fed. During the fed state, the body's priority is to get rid of that excess nutrient that's in the bloodstream. And so it does that at the expense of metabolizing fat, and then on, so that if you're eating every 4 to 6 hours and eat 6 times a day, essentially you're not burning fat at all. So in sort of wrapping this up, here's what it generally means, is that what ends up happening, and the reason why gaining weight is so insidious. The reason why you heard me from the very first TED Talk I give when I said that my 50 pounds of fat gain over 20 years was an extra 168 calories a week. And when you compare that to wiggling, climbing 73 stories, and only burning the calories in 3 1/8 Oreo cookies, you can see what happens, because every one of these meals can easily have tablespoon quantities of oil. And so for all the oil police and sugar police, etc., SOS, etc., all those people, they are directionally correct. They're not exactly correct, because if I put oil in a culinary quantity in a small teaspoon, I'm not going to really have any that's calorically significant. Not in that one meal. If I eat a meal every hour, that's a different thing. But if in that one meal or 2 meals a day, it's not going to make a big difference. And it's also not going to make a health difference, especially when it's a whole food, plant-based diet that has a teaspoon of sesame oil or 2 teaspoons of sesame oil and the whole recipe. And it's just on the outside of the vegetable, and it's there for the flavor and taste that we talked about with Ali Bouzari or Gary Beecham. The idea is that we can add these things in a culinary quantity and it's going to be just fine. At the other end of this spectrum is if we're putting oil on everything, olive oil, because you think the Mediterranean diet is pour olive oil on it and that makes it healthy, then you got a problem, because every time you eat, if you've absorbed that olive oil, then you're going to wind up gaining weight. You're going to wind up storing that oil temporarily. And now if you're in the chronically fed state, which means you get up in the morning, you have your coffee and cream, you decide, get a biscuit or get something on the way, have a meal, oatmeal or something, a healthy breakfast that you're starting your day out, right? And then you get to the coffee pot and you have a little snack there, or maybe some more cream or more whatever. Then you go to lunch, and then you have some lunch. And then in the afternoon, you're feeling a little low and slow. So you decide to go get a snack out of the snack machine, or somebody brings in donuts or cookies or something, and you go get something else, and then you leave and you go to happy hour on the way home and you have a little alcohol and a little bar snack food, and then on top of that, we were waiting, and then you go get dinner, and then you eat dinner, and then you get home, and a little bit later on you decide, I just could have a little noshy something before I go to bed. I'll just have some fruit, or I'll have some little bowl of ice cream, and then you go to bed and you can't freaking sleep because your body is burning off this stuff. Your body temperature is going up instead of going down, which you need to go to sleep, back to that cool environment of putting you to sleep. And now you're fed and your body's disposing of these calories 4 to 6 hours into your sleep. And then 2 to 3 hours later, you're waking up and the whole thing starts over again. Do you know how easy it is to get 168 extra fat calories a week in what I just described? It's really easy. And so that's why this paper is about why we gain weight, not how to lose it. I'm not talking about combining, food combining. If you eat your carbs and your fat together, you're going to get fat. That is directionally true, but it's not enough information. And I don't separate any of them. What I do is I limit the periods of the day that I'm in the fed state. And then I limit the overall quantity by the composition of the meal, using fats really in a more culinary sense. Nuts and seeds, avocados, coconut. I use olive oil. I use sesame oil, but only in quantities I need to hit the true culinary flavor of that meal, to get the right mouth feel. I'm never using more than a tablespoon. Rarely more than a tablespoon. There may be a couple exceptions, but that it's going to be a rare exception. Or I use a quarter or maybe a half. If it's a decadent recipe, like an appetizer sometime, I may have a half cup of cashews in that entire recipe, which is like 2 ounces. A quarter cup is an ounce, so it's like 2 ounces. And that's to share with everybody. I'm not going to eat it all. But even if I did, it's 2 ounces of nuts, and this isn't the problem. The problem is that first thing I said, that the body has to prioritize this stuff, and eating these mixed meals all day long, every day, even if the labels were exactly right and they're not, even if the serving sizes were exactly right and they're not, even if you're exercising every day, and you're probably not, but even if you are, it's easy to have a surplus of an extra 168 calories a week and to put this weight on over time. And that's how it should be. That's how it should be, because we evolved in a calorie scarce world. And it's sort of, yes, it's a just so story, but it kind of makes sense from an adaptive evolutionary perspective that appetite isn't a bad thing, and that storing fat, the most calorie dense part of the meal, the part that out in your backyard is going to be the most rare. Go out there and hunt for protein. It's in every plant. Go out there and find glucose and starch. There is every wood, everything out there is full of it. Go out and find lipids. Lipids are relatively rare, and so is alcohol, by the way. We make it unnaturally available. In nature, that ability to metabolize the alcohol, and it's on the fat side to the acetyl-CoA, but to metabolize that alcohol is probably just the leftover from fermented things, etc., a very small quantity. You don't find large quantities of alcohol in nature. We make that in sort of an artificial way, and I'm not invoking the appeal to nature versus whatever. I'm saying that we are able to unnaturally consume it, just like what we say here, which is in our first paper and in this paper, the only species that are obese and chronically ill are us and our pets, which we keep warm and overfed. And they get the same diseases as we do. Little doggy diabetes, little doggy heart disease, because we chronically overfeed our animals. If your cat or dog is overweight, it's your fault. People don't like to hear it about children, but it applies there as well. But it's your fault. And yes, obesity runs in family, including pets. Because why? Because we relate to each other with food. We're eating all the time together. And with this oxidative priority, what it suggests is that the expected outcome of eating these mixed meals with these small amounts of lipids that are efficiently taken in, especially when you're eating small, frequent meals, that your body's going to be storing those, and that the disposal of those fat calories is primarily dependent on the amount of time that one is in the fasted state. So when I wrote this, and at the time when I was actually researching that, intermittent fasting wasn't all the rage. But I would rather call it time-restricted feeding. So in other words, eating 1 meal a day or 2 meals a day, what does that do? Well, it means that your body's only dealing with processing meals for a shorter window of time, which means it can dispose of surplus calories. And those surplus calories in the rested state are, worst case, half of your energy burned. Or in best case, if you've actually been restricting your calories for some period of time in a diet, maybe 75 or 80%. And of course, in the case of the person that's doing the ketogenic diet and fat is a higher percentage at that point, it is, but it's not higher relative to the fat that's being input and stored and absorbed, because you're going to increase the efficiency that you're going to extract that lipid out of your digestive tract. So the end of all this is to say that meal frequency ends up becoming the most important thing. It becomes the most important thing. The more often you eat, the easier it is to gain weight. And of course, meal volume matters. And then the composition of that food matters. The high fat guys are right. The high carb people are right too. But they're both right for the wrong reasons. In one case, it's the body being able to have to burn these excess calories, or the high protein. We'll just throw them in there. I guess the high alcohol people don't get their fair share, but a lot of alcoholics are lean. And that's not because alcohol gets turned to fat. It doesn't. It's just that they'd rather have those calories. But what do you see? You see a lot of that characteristic red look in their face and that pink. What is that? That's the body constantly shunting blood to the surface of the skin because excess heat is being generated from all the alcohol they're drinking, and all the alcohol they're drinking needs to be exposed as waste heat. And so they get in this constant state of in this waste heat perspective. And if you've ever been around an alcoholic when they're sleeping, you know that their body is giving off a ton of heat, even when they claim they're not drinking. Well, you can, of course, smell it. But my point is, anybody that's been it knows exactly what I'm talking about. They're like a furnace sleeping next to you. It's hot. You can tell. And you know this too, because if you've been out drinking, you're sweaty, you're moving around. This is all of your body's way of getting rid of that excess alcohol. And so this is consistent across the board. It's consistent in time. It goes all the way back to Lavoisier. He measured it all the way forward to 100 years later. All of those great nutritionals do it, and I can measure it at my lab today. Prentice did a lot of work on this in the 90s and early 2000s. This is really very well produced data. But utilizing it is a little bit tricky, and it's really difficult with these people that are out there considering themselves authorities on oxidative priority and just getting this completely wrong, because this really, again, has nothing to do with disposal of the calories for losing weight. That's just a deficit. And of course, as long as we only look at nutrition as daily in, daily out, we heard from a evolutionary anthropologist last week that none of those Hasdas are thinking about what their nutrition is, and none of them are significantly deficient in anything either. And it's not because everything's natural, it's because it's just not that hard to get the nutrition they need. And so if you're in the chronically fed state, or if you have to balance your checkbook every single day and say, I'm not going to write a check more than what I deposited today, you're probably going to have a pretty good bank account. You're going to have a surplus. For most of us, we look at the account balance, which is more over a week or 2 weeks or months, or for some people, many months. But the closer you get to that balance having being just enough, the more dollars in and dollars out on a given day matter. The same thing goes for food. And that is, when you're looking at Ansel Keys' starvation experiments, this was taking healthy men and studying them down below a sub-level of body fat where they were actually in a huge nutritional bind. And then trying to compare that to somebody that has a flush bank account with 100 extra pounds. It's like comparing somebody at the lowest economic levels in a third world country with a billionaire. Yes, every dollar has the same value to those two people. But in terms of how they spend every dollar, the person who barely is making anything, their dollar matters more to them, even though the value that you buy with a dollar is the same. And that's the same as economic disparity is the same with a person who is overweight versus someone's thin. All these trainers are running around in the gym and they're saying, look at how I eat, look at what I look. Well, losing weight and not gaining weight are two totally different things, and this is why. So I hope that helps. If you have any questions, email me or message me on Twitter, Instagram. And thank you for joining me on this plant-based path to good health. It's always the food for your mind and body, so keep eating right.
Thank you for listening to Science and Saucer. For more details about the content in today's show or to contact Ray, please visit us at healthspansolution.com.
Welcome to the first day of the rest of your life.